Okay, we're ready now for lesson 7.4. You can see our title. We're going to be graphing rational functions. And this is going to be a process I'm going to walk you through. It's kind of a step by step. The beginning of this lesson, it's going to be important for us to identify areas of this rational function that are not graphable. We're going to get more into detail in that in just a minute, but kind of give you a little preview of where we're going. We've talked about continuous functions. You don't have to write this down, but here's an example of a continuous function. It just flows unimpeded from left to right, no breaks. Just I can put my pencil down on the left side and I never have to pick it up as I trace from left to right. Well, today you're going to learn about the occurrence with rational functions. You may have something called a vertical asymptote. We've talked about asymptotes before. Well, that represents a barrier that keeps our graph from flowing left to right. We call that a line of discontinuity. Discontinuity because it causes the graph to not be continuous. So instead of a free flowing from left to right graph, it would have to do something more like this because we cannot cross over vertical asymptotes. So it's kind of like a wall, and we'll just approach that vertical asymptote forever. We'll also have the occurrence of horizontal asymptotes. And that's the same idea. It's just that it's going to be a horizontal line that can, well, most of the time it can't be crossed. Horizontal asymptotes are a little bit weird. There are some rare occasions where horizontal asymptotes can be crossed, and I can let you know when that happens, but it's a rare occasion. And then we're also going to be identifying something called an oblique asymptote. That's just another word for slant. An asymptote line that does something like this. We're also going to have, in addition to lines that create discontinuity, there are points that create discontinuity, and those are called holes. So here's an example of a hole in a graph. It flows forever, but it comes to one certain point that we can't graph, and that represents a hole. So the beginning of our lesson will be, how do we know when these situations arise? So we know basically where we can't graph. And then we'll be able to actually come up with the graph that will be around any vertical asymptotes, horizontal asymptotes, oblique asymptotes, and then holes. So kind of a preview of where we're going. There's a lot here. For that reason, we're going to take 2 days on this. We'll get through our notes today. We'll get through some practicing today, and then we'll do some more practicing tomorrow. So let's get right to it. First of all, let's identify how we know if there is a vertical asymptote that we need to account for. A vertical asymptote, again, it creates a vertical barrier that we cannot cross. Now, that is true. Vertical asymptotes 100% of the time can never be crossed. Now, that's not true for horizontal asymptotes and obliques. There are some rare occasions where they could be crossed over, but you can take it to the bank. Vertical asymptotes never crossed by our graph. They're like stone walls that prevent any kind of passage. So here's how we know if we have a vertical asymptote. These are values, or another word for numbers, that make the denominator zero. All right, so these are just examples on how we can find vertical asymptotes, and then later on in the lesson, we'll actually put those on our graph. But first of all, you should be in factored form. Fortunately, this first function is already. I'm focused on the denominator only, okay? There are two numbers that would cause the denominator to be zero, and these two equations represent vertical lines. In this particular case, I would have two different vertical asymptotes that I would have to graph around. In other words, the graph really is undefined for all the points where x is 0. That's a vertical line, x equals 2. And here another line, x equals -3, the graph is undefined there because that each of those cause division by 0, which is mathematically impossible. Okay, the next function is not factored, so let's do that first. That should always be your first move in these problems. So that's the difference between two squares. And once again, I've got two vertical asymptotes. There are two numbers that cause the denominator to be 0. I would have a vertical line at x equals -4, and then another one at x equals +4. And then our graph would exist around those two lines. All right, let's take a look at this unique situation. I can't do any factoring here. So if factoring isn't possible and you want to know for sure if there is a number that would make the denominator 0, well, just make the denominator be 0 and solve for x. So when I try to solve this equation, I'm going to end up doing the square root of a negative number. So this is something to be on the lookout for when you're trying to find numbers that cause the denominator to be 0, and in the process you end up with I pops up. Well, that's just another way of saying there are no real numbers that cause the denominator to be 0, so we don't have any vertical asymptotes here. It's all about, for vertical asymptotes, it's all about numbers that cause the real numbers that cause the denominator to become 0. And make sure you factor first so you can see them easily. Okay, now let's talk about when we have horizontal asymptotes, those horizontal lines that cause a barrier. It causes our graph to not flow unimpeded forever. Well, horizontal asymptotes are quite a bit different. With horizontal asymptotes, it's all about the degrees. Of the numerator and the denominator. So let me just do a little refresher if you've never heard this word degrees. How do we determine the degree of a polynomial? That's basically what we have here. We got two polynomials being divided. That's what makes our rational function. The degree of the numerator is 2. So if you want to know what the degree is, look at the highest variable for, or the highest exponent for the variable. All right. So the degree of the top is 2. The degree of the bottom is 1. So this is a situation where the numerator, I'm going to say it like this, the numerator degree is greater than the denominator degree. So it's all about degrees. If this ever happens where the numerator degree is bigger than the denominator, then you do not have a horizontal asymptote. It doesn't really matter what it is. If this were x to the 4th and this were x to the 2nd, if it's bigger in any way by numerator over the denominator, then you don't have to worry about sketching and graphing around a horizontal asymptote. So that's situation number 1. Situation number 2, I still compare the degrees, but notice that they're the same. The top degree is 2, the bottom degree is also 2. So this is the scenario where the numerator degree is the same as the denominator degree. I'm going to say the horizontal asymptote like this, and then I'm going to explain. You're going to have a horizontal asymptote that will be the fraction a over b. And what I mean by a over b is if you just look at these lead coefficients, you're basically going to make an equation using the top coefficient over the bottom coefficient. So in this case, I'm going to have a horizontal asymptote that will be the line y equals 1/2. That's 3/6 reduced. All right, so recap. If the numerator degree is bigger, don't have to worry about it. If they're the same, you're going to make a fraction out of the lead coefficients, and that will be your horizontal asymptote. Let me just throw another one here. Let's change the problem a little bit. If this were 8 and this were 4, then I'm going to have a horizontal asymptote of y equals 2 because the degrees are the same, 8 divided by 4. Okay, everybody good so far? Any questions so far? It's a lot to take in, and in just a minute we're going to put it all together, and it's going to be a process that we're going to walk through, but we have to keep all of this stuff in mind as we walk through the process. All right, so let's take a look at the final situation. Looking at the degrees for horizontal asymptotes, it's always a comparison of the degrees. The top degree is 1, the bottom degree is 2. There's an understood 1 exponent here in the numerator. So here's the situation where the numerator degree is less. If this happens in the rational function that we're dealing with, it's always the same horizontal line. It's really another way of saying the x-axis, but technically it's the line y equals 0. So if your denominator degree is bigger, or you could say the numerator degree is less, whichever way you want to look at it, you'll always have a horizontal asymptote, and you can just basically draw a dotted line on top of the x-axis. Okay, so now you know how to spot vertical asymptotes, denominator equals 0, if they happen. Horizontal asymptote, it's always a comparison of the degrees. Now let's talk about oblique asymptotes. Your ability to do long division is going to really come into play here, because we have to know how to do long division if we're going to spot where an oblique asymptote happens. Oblique is just another word for slant. It's going to be a line. If we have it, it's going to be some sort of line, a y equals mx plus b. And the slope will be positive. All right, so it's going to be something like this. Our job is to find out what the y equals mx plus b is. All right, so we can sketch what the oblique asymptote. But first, let's find out if we have them. Here's what you're on the lookout for. You will have, if these two situations occur, first of all, we have to have the numerator and denominator are polynomial functions with no common factors. All right, what's that mean? Well, let me give you an example of rational polynomial functions. Well, numerator and denominator are both polynomials. So here's a situation where there are common factors. All right, I got everything in factored form. I notice that I've got x plus 2 that can cancel. Well, this is an example of having common factors, so I would not have to worry about an oblique asymptote here. All right, so here's a counterexample. I got everything factored. I have no common factors. Okay, now I've got the potential of having an oblique asymptote, but it's not just that. The next thing to be on the lookout for, in order to be an oblique, is the degree of the numerator has to be exactly 1 number higher. Okay, if it's this, I'll make this to the third. That's 2 degrees higher. I don't have to worry about an oblique. It's got to be exactly 1 degree more. Okay. X to the third over x to the second, x to the fourth over x to the third, okay, and couple that with no ability to cancel. That's another way of saying no common factors. Okay, so everybody good on, first of all, I mean, I don't want you to jump into long division if it's not really necessary. It's not going to be necessary unless both of these are true. All right, I'm going to try to save a little bit of time. Yeah. Question.
Does it have to, so on the first example you gave, there wasn't 24 degree, they both had a degree of them.
You're talking about this one over here?
The other one.
This one?
Yeah.
It actually is, because if I did multiply, this would be x squared. and then this would be x to the first. But yeah, that's what you're on the lookout for. It's got to be just exactly 1 degree. If it's 2 or more degrees, then you don't have to worry about an oblique. Good question. Anybody else? Okay. Let's just skip down to letter B. Okay. Let's see. I'm going to go ahead and factor. So this is plus, this is factors of 20 that add up to 8. Don't have any factors of 20 that add up to 8, do I? Positives, 4 and 5, 2 and 10. Doesn't factor, does it? Okay. So there are no common factors. So I'm going to jump into long division, and notice I'm dividing the denominator into the numerator. So here we are reviewing long division. This is one of the reasons why we had to cover it several weeks ago. So I divide the first term into the first term. It goes x times, multiply. All right, subtract. 8 minus 2 is 6x. Okay, now I'm dividing first term into first term, and that goes 6. Now, you don't have to feel like you got to take this all the way to remainder. Remember, an oblique asymptote is a y equals mx plus b equation. Well, we have it. Our oblique asymptote is going to be y equals x plus 6. You don't really need to go any further. You don't have to feel like you got to take it all the way to the end like we did back in chapter 4. Once you've seen what the mx plus b is, you're done. And you would graph this y equals x plus 6 line. It's got a positive slope. You just make it dotted when we do our graph, and you're good. Okay, questions there? Yes.
When do you enter something that?
Say it again.
When do you know how to stop?
When you get, you're looking for a y equals mx plus b. So when you get basically mx plus b, you're good. Yep. All right, all good? Questions? Okay, now let's get to holes. How do we know that we've got a hole in the graph? It'll be something like this, where a line continues, but all of a sudden it gets to a point and jumps. It's undefined at that particular point, and then it continues on from there. Well, you definitely want a factor. That's always the case. All right. And the occurrence of a hole, it'll always happen if we are able to cancel between the numerator and the denominator. All right, so this tells me I'm going to have a hole because I can cancel those matching factors. And where the hole exists, it exists at the x that causes that factor to become 0. So what happens here is this kind of complicated looking rational function that we thought we were going to have to maybe spend a lot of time graphing. As it turns out, it's actually the line y equals x plus 6. Here's the y, because these cancel. But we can't let it pass through the point 2, 8. You see where I got 2, 8? How'd I get 2, 8? Yeah?
Plug the 2 into the equation.
Yeah, I found out the number that I could plug in for x to make that common factor be 0, and then that gives me a point on the graph that really is undefined. We cannot let x be 2 because that causes division by 0. But the fact that I had a matching factor, now pay attention, we focused earlier on numbers that cause the denominator to be 0 are vertical asymptotes. Well, now I don't have a vertical asymptote anymore because I was able to cancel. Instead of a vertical asymptote, I actually have a hole in the graph. Okay, well, let me just change the problem a little bit. If I had this, I would have a hole at x equals 2, and now I would have a vertical asymptote at x equals -3. Okay, so another way of saying it is vertical asymptotes are numbers that make the denominator 0, and I wasn't able to cancel with the numerator. Holes make the denominator 0, but they also have a matching factor up in the numerator. All right, here's another one. I'm going to factor. All right, I thought maybe at first I had a vertical asymptote, but as it turns out, since I'm able to cancel, what I thought was a vertical asymptote is actually a hole. I'm going to have a hole at x equals 8. And it's going to actually occur in the line at the point 8, 16. I'm going to be graphing the line y equals x plus 8 with a hole at this point. So that's the only point where the line is not going to go continuously. Okay, so we've identified basically areas where we can't potentially graph. That's going to be up to you to know when you can graph in certain places and when you can't. And now let's kind of put it all together in sketching the graph of rational functions. The first thing you should always do, I've already said this, but make sure before we get into the steps, and this is a repetitious step-by-step process, I think if you do the same thing every time, step by step, it makes it easier to remember when you get to the test. I'm not going to provide the step 1, step 2, step 3 on the test. It's going to be up to you. But I would make this part of your routine because then it gets easier to remember when you do it on your own. But the first thing you should always do, if possible, is factor. All right, I got the factoring, the denominator is not factorable. So step 1, let's see if this graph crosses either the x or the y axis. And I gave you a little hint here if you forgot how to do that. If we want to find x-intercepts, we'll just take the numerator and set it equal to 0. So you can do either the red or the blue. I'm going to just do the blue as it's already in factored form. So this tells me that I'm going to have 2 x-intercepts, one at +3 and one at -2. So setting the numerator equal to 0 will tell you if your graph crosses the x-axis. So I'm going to go ahead and make a couple of points. There's x equals 3, and there's x equals -2. Now let's see if there's a y-intercept. We just put 0 in for x, all the x's. And again, you can use either the red version or the blue, it doesn't matter. But if I let x be 0, I get -6 on the top. I get +1 on the bottom. So that tells me, in addition to these 2 x-intercepts, I'm going to have a y-intercept at -6. So we definitely know our graph is going through those 3 blue points. All right, so that's kind of like where can we graph? Where's the graph going to go? Now we're going to find where we can't graph. All right, and I'm going to start with vertical asymptotes. Since I couldn't cancel, I'm going to have a vertical asymptote at x equals -1. That causes the denominator to be 0. So I'm going to go ahead and sketch x equals -1, dotted line. So that's a fence, a wall that I cannot cross. All right, let's check for horizontal asymptotes. This is where we compare the degrees. The degree of the numerator is 2. The degree of the denominator is 1. Since the numerator degree is bigger, that tells me I don't have a horizontal asymptote. But you're going to show this just so I know you checked. All right, let's check for oblique asymptotes. For an oblique asymptote, the degree of the top has to be 1 more, and I can't have any matching factors, couldn't cancel. So it looks like we are going to have an oblique. I'm going to come down here and we'll do the long division down here. All right, so x into x squared plus x. -1 minus 1 is -2x. Don't really even need to bring down the -6, but if you want. And now x into -2x is -2. So I have an oblique. This is the mx plus b. I'm going to have an oblique asymptote at y equals x minus 2. So let's just go ahead and sketch that while we're here. All right, it has a y-intercept of -2 and a slope of +1. And I know you don't have straight edges, but we'll just do our best to sketch out a dotted line. And I don't have any holes because nothing canceled. Holes would only occur if I was able to cancel between the numerator and the denominator. All right, let me pause for a second and make sure we're all together before we start actually coming up with points that do fall on the graph. So any questions so far? We basically identified where we can't graph, and now we're going to work on where we can. Any questions? Okay, so now it's going to be inputs, outputs. So we're going to be working with tables. Now, I always get the same question, how many inputs? Well, it kind of depends. There's no just one set number. It kind of depends on the problem. You're going to need to do a sufficient number to give you an idea of what the graph is doing. You don't have to go crazy, but I can't just say always do 3 or always do 2. It depends on every graph could be a little bit different. So it's really going to fall on you to make sure you feel comfortable. What I can tell you is this. I've got this vertical asymptote being sliced by this oblique asymptote. My graph is basically going to be divided up into 3 parts. Okay. I know that I can't cross this vertical, so my graph is going to exist to the left of this vertical asymptote. It's actually going to cross the y-axis there. I just need to know what's it doing from there. Is it following this vertical forever? And is it doing that? Or is it doing this? What's it doing on the left of that vertical? And then on the right of the vertical, is it here and here? So basically the vertical asymptote is a divider. We need to know what happens on either side because that's like a wall. What happens to this graph on the left of the wall and then what happens on the right. So I'm going to focus on the left of that vertical asymptote. We already know that at x equals -2, we got a point there. Let's input -3. And I'm going to turn it over to you at this point. You'll need your calculator. And it doesn't matter which of these versions you use, whether it's the red or the blue, doesn't matter. We're going to input -3. You do want to make sure, of course, that you put negative numbers in parentheses when you square them. And if you put operations in parentheses like this, you need to put parentheses around that denominator entirely if it represents an operation. Just my mental math, you can check me. I got -3 as an output. I got a question. Yes, sir.
Why do you plug in negative?
I'm just trying to find out what happens to this graph on the left of the vertical. And so that means choosing x's that go this way. And I already have -2. So I want to know, okay, well, what happens at -3? So we're basically focused on the left side of that vertical asymptote. Is that correct? -3? Okay. All right, so let's plot -3, -3. 1, 2, 3, 1. I'm going up. 1, 2, 3, 1, 2, 3. All right. Just for just to see, let's just go ahead and do -4. We'll keep going to the left and see if we can identify a pattern that's happening. So what do you get as an output if you input -4? Somebody want to give me that? Just let me know. Anybody got it? -14 thirds. You can do the decimal form. Who's got that? What do you got, Bill? Or Ben? What is that decimal, -14 thirds?
-4.6 reading.
Okay, so we'll just say -4.7. All right, so I think this is going to give us enough to tell what's happening to the left. So input -4, output -4, and a little bit more. So looks like I've got enough here. Vertical asymptotes are always going to be approached vertically, either going up or down. Looks like I'm going to be approaching that vertical asymptote forever. And then I'm going to hug alongside this slant asymptote forever. So I've got one of the pieces of this graph. All right. Now let's see what happens on the right side of that vertical. Well, we already figured, let's make our work a little bit easier. We know we're going to be crossing here and here. The y-axis, we came up with the y-intercept and the x-intercept. And I think that's going to be enough. We can just connect those two. Remember, you always approach vertical asymptotes, whether that's approaching positive infinity or negative infinity. And then I will be approaching this oblique forever. Let me just relieve the thinking of will I cross over an oblique? Okay, so here's how you can know for sure. Take the equation of the oblique and make it equal to the function. And I know you're thinking, how long is this problem? Well, this is part of lesson 7.4. Some of these problems can drag out. Let's do FOIL. So you're going to multiply by x plus 1 on both sides. So go ahead and do that. I'm just going to solve this. I let the oblique equation equal the function. I'm going to cancel the denominator. And let me see. Somebody feel confident about FOIL here? X plus 1 times x minus 2. What is that? I got it. You got it, Daniel?
X squared minus x minus 2.
Okay. All right, so here's how you know with confidence, because there are some occasions where obliques can be crossed. But if you notice, everything cancels and I'm left with something that's not true. That gives me confidence that the oblique cannot be crossed. If I got a solution here for x, then that's the location of where I would be crossing the oblique. All right, now we're done. Any questions? Do you like it? Okay. I always have to ask. One of these days, somebody's going to say yes. So far, after 35 years, it hasn't happened. So, okay, let's try this one. Walking through our process, we should do all factoring. So let's do that first. We can factor the denominator. That's the difference between two squares. That's supposed to be 2, not 4. All right, and now let's see if we have any x-intercepts. So that means we're going to set the numerator equal to 0. Make an equation. So since it's an even root, this is going to be plus minus, and you just estimate the decimal. So this is going to be plus minus the fourth root of 2. So if you're not sure about how to do fourth roots in your calculator, you have a button that looks like this on your calculator, where it's got a little asterisk there. Do y'all see that? So if you want to do a fourth root, you just do 4 and then hit that button and then put the number underneath. So that's a decimal. Just round to the nearest tenth. What would that be? Fourth root of 2. Somebody got it? Got it? Is it 1.2? Okay, we'll say 1.2 plus minus. All right, so let's just go ahead and estimate 1.2, negative 1.2. So we know we're going to be crossing x at those two places. What about a y-intercept? Can you tell where that is just by looking? You're going to let both the x's become 0. What do you get? Looks like 2, right? Negative 2 divided by negative 1, positive 2. So if you want the y-intercept, just put 0 in for all your x's and see what's left. Okay, now let's go to points and lines of discontinuity. So let's start with vertical asymptotes. I'm going to have 2. I'm going to have one at x equals negative 1 and x equals positive 1. Intercepts are just to the left and to the right of those two dotted lines. Do we have a horizontal asymptote? Let's compare the degrees. The top degree is 4, bottom degree is 2. Since the top is bigger, we don't have to worry about a horizontal. Do we have an oblique asymptote? No, to have an oblique, it would just have to be 1 more degree. So we don't have to worry about an oblique in this case. Do we have any holes? No, nothing canceled. All right, so we're ready. We just need a little bit more information. We know we're going to be crossing the x-axis here on the left of this. I'm starting from left to right. I'm going to see what happens here, what happens in between, and then what happens here. That's basically what we're going to be doing with our table. We got to graph around those vertical asymptotes. All right, so let's see. What about negative 2? Let's get an output for input negative 2. And if you're wondering why negative 2, well, that's the first negative number I came to as I walked to the left. So negative 2 to the fourth is 16, minus 2 is 14. Negative 2 squared is 4, minus 1 is 3. So the decimal form of 14 thirds
4.67.
4.67, 4 and 2/3. All right, let's plot that point. So negative 2, 1, 2, 3, 4. Let me erase my arrow here. 1, 2, 3, 4, 5. Just a shade below 5. Well, here's something that we know for sure. We are never going to reach a point where we eventually come down and hit the x-axis again. We're only hitting the x-axis in these two places. That's why it's good to come up with that first. All right, so it looks like if you want security, you could go ahead and do negative 3, But what's going to happen is as you choose inputs that are more and more negative, you're just going to be continuing to go in this direction. So we don't have to go crazy here. You do what you feel like you need to do. But if you did do -3, did anybody do that? Input -3? It's a pretty big number. That's 81 minus 2, 79 over 8. 79 eighths. So it's way up there. So I'm going to go ahead and complete this. Since I know we're never going to come back and hit X again, I'm going to, this time we'll be approaching that vertical, going down forever. All right, now let's think about in the middle. Since I don't have to worry about ever hitting the x-axis in between those two dotted lines, we only have two x-intercepts and they're not in here. Then what this is going to do, it's going to go through this point. It's going to be like a parabola. I'm going to pass through and approach going forever up. I'm going to pass through and approach forever up. And I can let that represent the middle part, since we know we're never going to come down and hit the x-axis again. And it's not 100%, but it's pretty common that for these fourth degree polynomial rational functions, there's typically symmetry. I mean, you got a clue that we have -1.2, +1.2. So basically we have symmetry on this side. It's just, that's terrible. The negative inputs that we used over here, we'll get the same result if we input the positives. So I'm going to do +2, 4.67. And wow, that's not real good, but you can do better with your pencil. I should show symmetry here. It should be like a mirrored image. So you have this left piece that has to stop at that first vertical asymptote. You have a piece that is in between the two vertical asymptotes, and then you have the right piece over on the right side. Okay. Questions? Is it as bad as you thought or worse? Yes.
Will there be like a required amount of input that you have to put?
I am not going to require it, but you know, if you shortchange it and it ends up costing you on your graph, then obviously, you know, you'll lose some points. But I'm not going to say always have this number because it really depends on the problem. Yeah.
If we have a big asymptote, we always need to check and see if it's possible.
I would, because they can be crossed. Yeah, I would definitely check. And then that rules it out. If you rule it out, then you can always just approach the oblique without having to feel like you got to keep testing to see if you cross it. So does that answer? I think that's a good thing to do. It'll save you some work in the long run, potentially. All right, good questions. Let's try this one. Let's start with x-intercepts. Do we have any? Set the numerator equal to 0 and solve. Well, 4 is never going to be 0, so we don't have any x-intercepts. What about y-intercepts? Let both x's be 0. And then what's the result? -2/3. Everybody see that? So you literally just let these become 0, and then the denominator becomes -6. 4 over -6 reduces to -2/3. All right, so I'm going to guesstimate -2/3 on the y. So this graph is never crossing the x-axis. Keep that in mind. That'll help. All right, let's find lines of discontinuity, starting with the vertical asymptote. Looks like I'm going to have 2. Sketch them. So what this amounts to is, once again, we're going to have a graph that exists in three separate sections. To the left of this first vertical asymptote, in between the two, and then over here to the right. So we just have to find out where it actually lives in those three sections. All right, let's see, do we have a horizontal asymptote? Well, the degree of a constant is 0. The bottom degree would be 2. If you did FOIL, you'd have x squared. So what happens if the bottom degree is bigger than the numerator? It's always the same line. Y equals 0. So I'm actually going to do a dotted line on top of the x-axis as a reminder. And this is another answering Houston's question, which was good. Do you remember how we checked to see if an oblique could be crossed? We take the oblique equation, make it equal to the function. You can do the same thing with horizontals. You just let 0 be here, and that's probably something you can do mentally. If you multiply both sides, if you let 0 be here and you multiply both sides, what would you end up with? If you multiply both sides by the denominator. Because 0 equals 4, that's not true, so you don't have to worry about crossing the horizontal here either. There are some occasions, rare occasions, where they can be crossed. Well, now we don't have to worry about it. Okay, so now the question becomes, on this side of the vertical, I'm not crossing the x-axis at all. So the question becomes, is the graph up here or is it down here? The only way to know that is to start testing numbers. All right, so the first number I come to, let's see, that's 1, 2, 3, -4. Input -4 and see what you get. -4 minus 2, -4 plus 3. Looks like positive 2/3. Is that what you got, or 0.67? Well, right, really, that's all I need. All right, I'm never crossing the x-axis. I can't cross this, well, I just did. I can't cross that vertical asymptote. So really, here's another case where you can use decimals or fractions. I'll try my best. I'm going to approach and approach. And that's one of our pieces. In between, if we want to get a little more exact, we know we're going to be crossing here. Let's just go ahead and do -1 so I can know a little bit more detail. So let's input -1 and get a point. So I'll just do my work up here. -1 minus 2 is -3. -1 plus 3 is +2. Looks like it's the same thing. That it's going to be -2/3. And I'm going to let that be. I know I'm not crossing x, so that means when I go through these 2 points, I'm basically going to be following these 2 vertical asymptotes. I'll be approaching both of them forever. And now let's see what happens to the right. So let's input +3. That's the first x I come to the right of that vertical asymptote. So what do you get when you input +3? 4 over 3 minus 2 is 1. 3 plus 3 is 6. Looks like a common theme. So I'm going to input or write 3 up 2/3. And because I know I'm not crossing the x, I can never cross the vertical. That's always impossible. There's our graph. Okay, do you have any questions, anybody? All right, we're gonna keep on going. I've got a little bit more time. Let's try this one. X-intercepts. Well, if we're not sure, just make the numerator equal 0 and solve. So if I've got an x-intercept of 0, that means I'm going to have a y-intercept of 0, which is another way of saying the origin. So we're going to be crossing through the origin in this graph. Let's find our lines and potentially holes of discontinuity. So we have a vertical asymptote at x equals positive 2. That causes the denominator to be 0. We can't do any factoring, so we'll just jump right into it. Horizontal asymptote, compare the degrees. The top degree is bigger than the bottom, so don't have to worry about it. Oblique asymptote, do we have an oblique? Well, the top degree is bigger by 1. Can you tell just by doing mental long division what that's going to be? Looks like it's going to be x plus 2. And if you want to check and make sure that we're not going to be crossing, I think you can probably tell that we're not. I'm going to try to save a little bit of time. Our class period's getting away. Let's go ahead and sketch y equals x plus 2. And don't have any holes because nothing canceled. I'm just saying not applicable. All right. Well, let's make this easy on ourselves. We know that we're going to have a piece that exists down here because I think you can tell that if you let x plus 2 equal x squared over x minus 2, well, let's see what we get. X squared minus 4. When I do FOIL, I just multiply by x minus 2 on both sides. The x squares cancel, so 0 does not equal negative 4. I don't have to worry about crossing the oblique. Never cross verticals. So we could do a rough sketch. I'm just going to get a little more specific. I'm going to find out what comes out if I let x be 1. That's easy math. Negative 1. And I'm going to let that suffice. I'm going to be approaching this vertical forever, going down. And since we know we're not going to cross the oblique, I'll just follow that forever, going this way. Okay, so you're always looking at vertical asymptotes. They're kind of they're the main dividers. We know what's happening to the left of the vertical. Let's do an input of 3 to tell what's going to happen on the right side of that vertical. So what do you get if you input 3? It's like 9 over 1. So that's the 0.39. 1, 2, 3, 2, 3, 4. I think that's 9. And get a little more definition. Let's input 4. It's easy math. What do we get when we input 4? 16 over 2, that's 8. So we can kind of see it's taking shape now. So it's kind of parabolic shaped. And we just follow those asymptotes forever, going through those 2 points. Okay, questions on that one? You're doing great. Any questions? Yeah?
How do you know, like, which side the thing will have one pretty good?
I want to make sure I understand your question. The vertical asymptote is really the divider.
Yeah, like, how do you know you won't have one on the right of it?
On the right of, like down here, you mean?
Yeah,
Well, we proved earlier that we're not crossing that oblique. So if I have a point up here, the only way to get down here is if I crossed the oblique asymptote.
so,
So that's why I was saying to Houston earlier, he had a good question. Doing this little process will save you a lot of time. If you know you're not crossing an asymptote, then you can just pretty much stay within that area. You're not coming out. Yeah.
why would you not check on the left side of the?
Over here, you mean? Well, we knew we had to cross here because we came up with this early. And if I'm crossing through the origin and we know we're not crossing over the oblique, then I don't need to check anything up here. It's kind of like I've got two fences that I've got to stay between. If I cross through this, in order to get up here, I would have to cross over that oblique, and we already proved that that's not going to happen. Does that answer your question? Yeah.
What was the process you used to prove it?
You take your oblique equation and just let it go in for f of x. You basically just take x plus 2. I did it right here. I let x plus 2 equal the function, and then multiply by the denominator. And if you can't solve it, it ends up with being something false, then that tells you you're not going to cross it. Yeah. All right, I got to hustle. Let's do some where we get into some holes. We haven't seen any holes examples yet. These are nice. This is a good way to end the lesson. Trust me. Okay, let's do some factoring. So in factoring, we basically reduce this, if you want to think of it that way. We've taken this complicated looking function, and it turns out that we're going to be graphing y, or f of x, equals x plus 6. This is just a linear function that's going to have a hole in it, and it's got a hole at x equals 2. So I'm okay at this point. If you want to go ahead and find x and y intercepts, that's fine, but I'm really okay with you graphing like you know to do, y equals x plus 6. We just have to remember that we have a hole, and it should be at the point 2, 8. So just make sure you understand how I got 2, 8. 2 makes the common factors become 0. And if I put 2 in for x, I get 8. I'm basically doing f of 2. So if you want to start there, and there's a hole at 2, 8, and then we'll just make our line go on either side of that. And there's no need for a table on these. All right, let's try this one. Let's do all the factoring we can. Look for opportunities to cancel. That tells us we're going to have a hole. So this turns out to be y equals x plus 4 with a hole, since we canceled. And it would be at 4, 8. One, two, three, four. 1, 2, 3. So I'm going to go ahead and put a hole there. And just draw y equals x plus 4 on either side of it. It basically jumps over that hole. I'll try my best. That's terrible. Okay. I think we're done. I think I've given you enough. For tonight,